Hello and welcome to helpyourmath.com. In this video, we are going to look at adding and subtracting radical expressions where we're going to have to simplify before we can combine. So when and how can we add or subtract radical expressions? When the radicands and the indices are the same. So they both have to have that same index, whether it's a 2 or a 3, and then they both have to have the same radicand, the same thing within the radical. If they have that, we would combine them by combining the coefficients of the radicals. So we almost treat the radical as a variable, and it would be the same way if we were adding two variables. 2x plus 3x is 5x. 2 root 7 plus 3 root 7 is 5 root 7. And a pro tip, since we can only combine when the radicands are the same, start with the one that looks like it's going to be the friendliest. So if some of them look a little bit intimidating, we can actually kind of use a strategy here where, okay, we're going to do the one that looks like it might be the simplest, because what we know is whatever's stuck under the radical, the other factor of each radicand should match that factor. And so we can kind of use that as a hint to help us along the way. Let's just review how we would simplify when we have an index of n. So when we have numerical radicands, this would be like n root of whatever. What we're looking for is we're looking for a factor of x, but remember x is going to be a number, that is a perfect power of n. And when I was doing the simplifying radical expressions video, I had a whole list of perfect squares, perfect cubes, perfect powers of 4, perfect powers of 5. You may want to reference that list. Once you've identified if there is such a factor, then we're going to write that number as that factor times whatever it takes to get back to where we started, and then we'll take the nth root of the perfect power of n, and we'll leave whatever's stuck under the radical. So for example, if we have the fourth root of 80, what we're looking for is a perfect power of 4 that's also a factor of 80. We might want to start with a list of the perfect powers of 4. I like to start with 1, except we're never actually going to use 1. 2 to the 4th is 16. 3 to the 4th is 81. We're already bigger than the radicand, so we can stop. So if 16 is a factor of 80, then we can simplify this radical. And 16 is a factor of 80. It's 16 times 5. So we would say 16 times 5. And then we can actually do the fourth root of 16. Since 16 is 2 to the 4th, we could say, okay, well, 2 to the 4th, the 4 and the 4 would cancel. The fourth root would cancel. The fourth root of 16 is 2. And this fourth root of 5 would be left under the radical. So that's how we simplify when we have a numeric radicand. If we have a variable radicand, what I like to do is I like to look for the largest multiple of the index that would go into the exponent provided. So for example, if we had the third root of, let's say, x to the 17th, what I'm going to look for is I'm going to break up this using, or kind of like undoing, the same base multiplication. So what I know is that I'm going to reassign this as x to the something times x to the something, where they're going to add up to 17, because then if we combine them, we would get back to x to the 17th. However, I want one of these to be the largest multiple of the index, the largest multiple of 3, that's less than 17. And the largest multiple of 3 would be 15. So this is accounting for 15 of the 17. There would still be 2 left over. And then we would have the cubed root of x to the 15th times the cubed root of x squared. And to simplify, when we do have a variable radicand, is we would take the exponent and divide it by the index. So 15 divided by 3 would be 5. So this becomes, this simplifies to x to the 5th. And then under the radical, we would still have that cubed root of x squared. All right, so let's get to adding and subtracting. In our first example, we get a little bit of everything. We have numeric radicands, we have variable radicands. Now we have to decide, okay, I assume that this problem was created so that it'd be able to actually subtract these. Which one looks like it might be friendlier to work with? And there's no, you can say whichever one. This is strictly your opinion. If you just want to go with this one, maybe you think 80 looks a little bit friendlier. Great, let's start with that. These are square roots, right? There's no index given, so it's assumed to be a square root. So we're looking for our perfect squares. Perfect squares, that's 1, 2 squared is 4, 3 squared 9, 16, 25. I probably don't need to go bigger than that. And we'll start by simplifying this. So this is like two problems rolled into one. We're focusing on simplifying under the radical, so the coefficient's just going to hang out until other things join it. So what's the largest perfect square factor of 80? You might recognize that 4 is a factor of 80, but the biggest one is actually 16, like we saw in the last example. 16 is a perfect square. It's also a perfect power of 4. So I'm going to think about breaking up 80 into 16 times 5, like I did in the previous example. A is just going to be stuck, right? That's just a to the first. We're not going to be able to take the square root of that. And we'll look at B. So with B, we want the biggest multiple of 2 that's less than 3. That's going to be 2 itself. I guess I should bring down the A. Poor A is just hanging out there like, wait, I'm here too. And now we're going to take the square root of what we can take the square root of. So the square root of 16 is 4. 4 is going to join the 3, so we're going to multiply those together, and we get 12. The square root of 5, so I'll just leave a little space. We have a 5 left under the radical. A is left under the radical. The square root of B squared is B. Oh wait, but I have this A squared already out here, so I'm just going to put A squared, and then I'll put the B, just so that way I have my variables going in alphabetical order, and this other B will just hang outside, or inside the radical. Okay, so now I know what I'm expecting. I'm expecting this radicand to match the 5AB. Let's make sure that it does. So we have this minus 5b that, again, we'll deal with after we simplify. And then 45, well, we're expecting one factor to be left is a 5. 5 times 9, yep, 9's a perfect square. I see it on my list right here. A to the 5th, we're going to break up a to the 5th into a to the 4th because that's the largest multiple of 2 that's less than 5. So this would be a to the 4th times a to the 1st, and then b is just going to be stuck there, right? We're just going to have that b. Okay, so now let's clean this one up. We're going to have minus. What's going to happen here? We're going to take the square root of 9, and the square root of 9 is 3. 3 will join the 5. 5 times 3 is 15. That looks not great. Hold on, I'm going to just say the square root of 9 is going to join the 5. I'm going to set up this radical and put that 5 underneath it. The square root of a to the 4th is a squared, so a squared is going to join our friends outside the radical. This a is stuck under the radical, this b is stuck under the radical, and we'll bring this b down. So a little bit of, making sure everything works. So we do have the matching radicands, we have the 5ab, but also the variables in front should also match a squared b, a squared b. That's good. If they didn't match, we would be stuck. We wouldn't be able to combine these. But we can, and we combine by combining the coefficient. I have 12 here. I have minus 15 here. So my final answer will be minus 3a squared b times the square root of 5ab. And there it is in simplest form. For this next example, we're trying to subtract these two radical expressions that have indices of 4. I'm going to just go from the left because 32 is a smaller number to work with, and I might list some perfect powers of 4 to look for those factors within 32 and 162. So 1 to the 4th is 1, 2 to the 4th is 16, 3 to the 4th is 81, 4 to the 4th is 256. Okay, so 16 goes into 32. This would be 16 times 2. So cleaning up this first radical, we have the 5 times the 4th root of 16 times 2. Well, the 4th root of 16 is 2, so a 2 is going to join the 5 out in front, which will make 10, and this other factor of 2 is stuck under the radical. So there's my hint. This should be something times 2, that something should be a perfect power of 4. 162 divided by 2 is 81, which is on my list, so I feel good about that. And then I have that 2 in front, 4th root of 81 times 2. Well, the 4th root of 81 is 3. 3 will join the 2 out in front, so that's going to make 6 when we multiply them. And that leaves me with 4 times the 4th root of 2. Are you getting the hang of these? Let's see. I suggest pausing the video, see how you do with this one. Okay, for this one, I actually probably would start with this 24. 24 looks nice. We do have indices of 3, so we're looking for perfect cubes. 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. We can probably stop there. So looking at this, I'm going to start with this last one, this minus w times the cubed root. So 24, I'm looking for, 8. 8 times 3 is 24. I can take the cubed root of 8. That's going to be a 2 out in front of the radical. So we'll have minus 2w. The w is stuck under the radical, and so is that 3. Okay, and then I'm just going to go from right to left. So I'll work on this middle one next. And again, what am I expecting? I'm expecting that 81 is going to be 3 times a perfect cube. Otherwise, I won't be able to combine these. So let's see. So if it is 3, that would be 27 times 3. And 27 is on my list, so it does work out. The cubed root of 27 is 3. So that cubed root of 27 joins the coefficient of minus 4, making minus 12. This w also is just stuck under the radical, so we have w here. And then we have the cubed root of this we took, 3w. So far, so good. How about this very first one? We are expecting a 3w left under the radical, so we have 7. And then we have the cubed root of, this would be 3 times 125. Which, of course, if you're not sure, you can always consult a calculator. And then w to the 4th, I need to split up. I want to write w cubed, so that way it's a perfect cube. And that'd be w cubed times w. So 125, the third root of 125 is 5. 5 times 7 is 35. And then the cubed, oh wait, I need to make space, don't I? So then we have the cubed root, we have this 3. The cubed root of w cubed would be w. And then this w is stuck under the radical, right? This one just comes down. Okay, so now I have w cubed root of 3w, w cubed root of 3w, w cubed root of 3w. Great. We're going to combine the coefficients. That's 35 minus 12 minus 2. 35 minus 12 would be 23. 23 minus 2 would be 21. So our final answer, 21w times the cubed root of 3w. Boom. In our last example, try this one on your own. See how you do with those 4th roots. So I'm going to start by writing some powers of 4. We have 1, 2 to the 4th is 16, 3 to the 4th is 81, 4 to the 4th is 256, 5 to the 4th is 625. No radicands are bigger than that, so we're done. Which one looks friendlier? I seem to really have a thing for 80, so I'm going to go with 80. 80, we might recall from the very beginning, and the first example is 16 times 5, and 16 does appear on my list. So I'm going to start over here with this minus 2 times the 4th root. I'm going to break up 80 into 16 times 5. Now I want to write m to the 9th as m to some multiple of 4. That would be 8 times m to the 1. That way I can just take that power of m. And then n to the 14th, I'm going to think about as being n to the 12th times n squared. Eek, this one's getting away from me. Okay, and now we're going to take those perfect powers of 4. So the 4th root of 16 is 2. 2 joins the minus 2 in front via multiplication, so we get minus 4. And then under the radical, I don't know how much space I need, but we're going to put that 5 there. Here we have m to the 8th. The 4th root of m to the 8th, remember we're going to divide the exponent by the index. 8 divided by 4 is 2. So an m squared will come out of the radical, leaving behind that m to the 1st, which I can just write as m. N to the 12th, 12 divided by 4 is 3, so this becomes n cubed. And then the n squared is stuck under the radical. So if we're going to be able to combine these, we need what's in front of the radical, the variables in front, to be m squared n cubed. It looks like we already have an n cubed. And under the radical, we're looking for 5mn squared. Okay, so looking here, we have 3mn cubed times the 4th root. So we're expecting this to be 5 times something. Well, what times 5 gives us 405? That must be 81. Yeah, that works. And 81 is a perfect power of 4 because that's 3 to the 4th. We're going to break up m to the 5th. I want to write m to the 5th as m to the 4th times m to give me that multiple of 4. M to the 4th times m. Dear. And then n squared will just stay n squared. Okay, so now when we take the 4th root of 81, that becomes 3. 3 times 3 is 9. And then left under the radical, we do have a 5. The 4th root of m to the 4th will be m, but that's joining an m that's already here, so that's going to be m times m, right? This is going to add an m out here. M times m is m squared, which is kind of what we were expecting. I don't think, and then m is left, and then n squared is stuck under the radical. We'll bring down that n cubed that was already part of the coefficient. We do have the matching variables in front, the matching indices, and the matching radicands. We're ready to combine. I have 9, I'm taking away 4. That leaves me with 5 m squared n cubed times the 4th root of 5mn squared. Nailed it. These have been examples of adding and subtracting radical expressions when you have to simplify first. Thank you for stopping by.